Module 11.1 Source Filter Theory. As this course has woven a path through many different topics, it's now time to find a unifying theory to make all the pieces fit together and explain why things sound the way they do. Early on, we spoke about the four sources of sound: vibrating bodies, changing airflow, sudden large changes in temperature, and supersonic flow. And we've looked at the fundamental frequency and harmonics in some simple vibrational systems: the Helmholtz resonator, the string, and the tube. Things get much more interesting as we start considering real-world sound production. There are two parts to understanding what makes up a sound. One, the production of sound, and two, the use of resonators or filters to shape the amplitudes of the frequencies that make up the original sound. Let's look at a tube. If I just blow into the room, you hardly hear anything. The blowing of air is a changing airflow. It's a non-periodic, non-repeating sound wave. Most non-periodic waves contain all frequencies, so if we did a frequency spectrum analysis, it would include all frequencies. The technical term for a sound like this is noise. This is different from the term noise we used in Module 8, which refers to loud or undesirable sounds. There are several types of calibrated noise. White noise contains all frequencies at equal intensity. Pink noise has equal energy per octave. Since each successive octave band has twice the bandwidth of the previous octave, the energy or amplitude has to decrease by half for each octave. So pink noise will sound duller than white noise, since the higher the frequency, the lower the amplitude. We generally use pink noise in acoustics because this corresponds to how we perceive sound. Now, back to the blowing air. If I blow air over the top of the tube, the sound changes. This is because certain frequencies of the sound of the moving air are amplified. As we've learned, those are resonant frequencies of the tube and are related to the length of the tube. The same thing happens with this spinning tube. The air moving over the open end excites the resonant frequencies of the tube. If I spin the tube faster, air passes the end of the tube at a faster velocity and the frequency of vibration will increase. At a certain point, I'll be fast enough that the vibrations are higher than the first resonant frequency, and the next resonant frequency of the tube will be excited. So what we are seeing here is a source that has many frequencies, the moving air, is having certain frequencies amplified by the tube. Let's now look at a vibrating body, specifically a vibrating string. Here I have a monochord, a string that is stretched tight and divided by a bridge. As I pluck the string, it makes a sound, but not a very loud sound. Now, listen to what happens when I put the monochord on the floor and pluck it. What did you hear? Now, let me place it on the bottom of this piano on the soundboard. What is happening? When I pluck the string while the monochord is in the air, we're hearing the string vibrating and nothing else. When I place it on the wooden floor, the vibrations from the string are coupled to the floor, and so the floor also vibrates, amplifying the string vibrations. When I place the monochord on the soundboard of the piano, the same thing happens, but the sound is louder and richer because the soundboard is designed specifically to amplify vibrations from piano strings. So, with musical and vocal sound production, the sound sources are changing airflow caused by blowing air, buzzing lips, vibrating reeds, vibrating vocal folds, rubbing or plucking strings, scraping, striking, or beating of a physical object that sets it into vibration. These sources contain a large number of frequencies, and those frequencies are then shaped by the physical dimensions of the cavities, the violin body, the bassoon tube, the timpani bowl, the oral and nasal cavity of a vocalist, that shape the frequency spectrum of the source of the sound. The term we use to describe all of this is source filter theory. In the simplest of terms, source filter theory says that the sound we hear is the result of a sound source being filtered by a resonant body. This shaping of the sound is not only for musical instruments, but for most of the sounds that we hear. The geometry and reflectivity of the surfaces of a room will affect the sound. The shape and materials that a speaker is made of will affect sound. The more frequencies a sound source has, the more effect the filter has on shaping the sound. Noise, square, pulse, and sawtooth waves are rich in frequency content, and so they are good sources of sound. Triangle and sine waves have very little, if any, harmonic energy, and so tend not to be good sources of sound. A filter will not change the timbre of either sound very much. One related note. Pulse waves have all harmonics at all frequencies. Remember that period and frequency are inversely proportional since F equals 1 over T. Now, imagine that you have a 100 Hz pulse wave. Each pulse would occur at 0.01 seconds, and you'll have a harmonic every 100 Hz. Now, imagine we've doubled the period so that there's one pulse every 0.02 seconds. Since the period has doubled, the frequency will half, and so you'll have a harmonic every 50 Hz. Let's do the same thing again. There's a pulse every 0.04 seconds, and there will be a harmonic every 25 Hz. If we carry this out to its extreme, we will have just one pulse. The period would be infinite. As the period got longer, the difference in harmonic frequencies decreases. So for a single pulse, you would have a harmonic at every frequency. So a single pulse contains all frequencies and would be an excellent sound source. When we think about percussion instruments, striking the instrument is applying a pulse, and therefore introducing all frequencies to the instrument. Similarly, plucking a string applies a pulse to the string, exciting all of the string's resonant frequencies. SEA majors, this is the concept behind impulse response. If you introduce a pulse into a system, you can know how it will respond to every frequency. This is the basis behind convolution reverb and many software emulations of hardware processors. For the remainder of this course, we will see how the sounds of different musical instruments and the voice are created by their sources and filters.